Here's a concavity. It's a feature of the graph that shows whether or not it is an upturn or a downturn in it. Okay, here's a picture of a graph in here. We have two of them here. Here's the graph itself. It's this part in here, and here's this one over here. Okay, this is an example of a graph that has concavity down. This one has concavity going up. And it also can be taken as an interval for which the first derivative of the function f is decreasing. And over here, the first derivative is increasing because as you move left to right, the slopes are getting higher, they're getting bigger. Here, as you move left to right, they're getting smaller, closer to zero, and then become negative over here. Okay, let's look at how to determine that in here. Okay, this is it here. We'll look at this. If your second derivative is positive, then you have concave up. If your second derivative is negative, you have concave down. Okay? That's based on the increasing, decreasing nature of the first derivative. Now, here's an example. First thing we're going to need is a derivative. I'm going to write this like so, just because it's easier in this case, not to use the quotient rule. So bring down -1, then you'll have an x squared plus 4, -2, and then times a 2x. That's the chain rule. So that's a -6x over x squared plus 4 quantity squared. Now you'll need another derivative. So f double prime. Here I'm going to use the quotient rule. So I have a -6 times the denominator minus the denominator's derivative, which is 2, then x squared plus 4, so the 1, and then times, see if I get a little more space here, times, I'm going to have to put it over here, times, I need a 2x, that's the derivative of the inside, and I also need the original numerator, which is a -6x, and then all of that stuff divided by the denominator squared. So it looks like this. Now if we reduce that, we'll pull out a -6 and we'll pull out an x squared plus 4. That leaves behind an x squared plus 4 and a minus 4x squared, like so, which is x squared plus 4 over x squared plus 4 to the 4th. And then that becomes, let's see, we'll do a little canceling there. Looks like we're going to have a 4 minus 3x squared up top and an x squared plus 4 to the 3rd power down here. Okay, now that's our second derivative. And to determine what the signs are, essentially we'll look for the changes in sign, which may occur when it has a 0. So we'll set it equal to 0, and that really means just looking at that quantity inside there. When is that 0? Well, 4/3 equals x squared, so x is plus or minus 4/3, which is plus or minus 2 over root 3, which is plus or minus 2 root 3 over 3. Okay, so we need to now test. Let's go in. Let's build a small chart. And we have 2 test points. We have a -2 root 3 over 3, and we have a positive 2 root 3 over 3. They're not test points, but those are our partition points, and we're going to check the signs around these 2 numbers. We know it's 0 right at the numbers. We want to know the signs to the left and to the right. So pick something convenient. Let's see if that were 2 let's say negative root 2, you could say, over here. Because if this is a little bit bigger than 1, in fact, let's do this. Let's keep it simple. Don't have to use a root. I can just use a negative 2. And here I can use a 0, and here I can use a positive 2. Okay, so for sure, my negative 2 is less than this. Root 3 over 3 is definitely less than 1. So let's go ahead and check those numbers. Okay, so down here now, let's see. Change that. Okay, so now over here, there it is. Okay, so I need f, what is it? F double prime of negative 2, and I'll use this version over here. So I see I have a negative 6 with a 4 minus 12 over something positive. The denominator is positive. I don't even know what it is, but I mean, we could check it, but it's positive. Numerator is positive. So we have positive here. So that means it's concave up. Okay, we'll just say C up. Okay, and when it's 0, f double prime 0 is negative. Okay, because the negative 24 over something positive. It's actually 4 to the third, but it is definitely negative. So now we've got negative in here, which means concave down. And when we're positive again over here to the right of that radical at 2, we have negative 6 with that same number, 4 minus 12, and then over that positive number. So it's positive again. So we're C up again. So what we have is some changes. You can see from here, we can summarize from the table. We can say concave up from, well, with negative infinity up to negative 2 root 3 over 3. Okay, unioned with 2 root 3 over 3 out to positive infinity. C down would be the in-between, negative 2 root 3 over 3 to 2 root 3 over 3. So graphically, you don't need to do a graph. I want to show you a little bit. What it appears that we have is this at, let's see, and let's say that's a 1 and this makes us a 3/4. So at x equals 0, we get a 3/4. That's from the original function. You can see that. When x is 0, you have a 3/4. Okay, and we have these 2 points which are over here, approximately. That's about 2 root 3 over 3, and someplace in here I don't have the height of it, but what's happening is, and there's another one over here. You know what? My scale is off. Let me fix that. I want to try to be a little bit accurate here. If that's 1, then this is about it here. That's 2 over 3 over 3. And this is the minus 2 over 3 over 3. And you have a point somewhere over here, another one somewhere over here. And the graph is kind of coming together like this. So you can see how the concavity is changing at that point right there. And it's hard to see if you weren't looking for it, but you could see that concavity is down in here, and then all of a sudden it becomes concave up over here and over here, and it heads down toward the x-axis like that. Never touches it. It just keeps getting closer to it. So you see the root intervals of concavity there.